Welcome to the NPU Enhanced IoT Edge Revolution for 2025, where we explore how integrating NPUs into everyday devices unlocks smarter, faster, and more efficient edge AI. In this talk, we'll trace how embedded NPUs enable on-device inference, reduce cloud dependence, and drive measurable performance and battery life gains across a range of IoT applications. Here we look at NPUs as domain-specific accelerators. They optimize matrix, multiply, accumulate operations for AI workloads while dissipating only milliwatts, delivering orders of magnitude higher efficiency than general-purpose CPUs or DSPs. Offloading CNNs and transformers to an NPU frees CPU cores for real-time control, extends always-on sensing battery life, and gives strategic edge advantages in performance and longevity. NPUs span a broad market from ultra-low power wearables through mid-range industrial vision to high-performance SoCs that handle transformers, illustrating a power and performance spectrum. Heterogeneous die architectures combine Cortex cores, ISPs, DSPs, and NPU subsystems, so developers can tune silicon for audio, vision, or multimodal workloads, matching power budgets and flexibility to the target use case. Deep NPU integration on SoCs pairs an embedded NPU with a unified memory cluster to eliminate external DDR traffic, dramatically cutting latency and power. Tight coupling reduces memory round trips by roughly 70%, enables sub-100 milliwatt keyword spotting, and lets ARM cores stay in deep sleep, while the NPU handles sensor pipelines and instant actions. Mapping AI workloads strategically places CNN feature extraction on NPUs, post-processing on DSPs, control loops on microcontrollers, and heavy training to the cloud, which optimizes throughput and power. Dynamic governors shift between a high-performance 400 GOPS peak mode and a 10 GOPS whisper mode to balance thermal limits and battery life, delivering adaptive efficiency and longevity. Maximizing on-chip efficiency relies on memory tiling, double buffering, and activation reuse to keep weights in local L2 and reduce external bandwidth. Compile time scheduling interleaves DMA transfers with compute-to-mask latency and maintain continuous data flow, enabling models to be squeezed into on-chip memory and achieve target frame rates on constrained IoT devices. Safety-ready RTOS integration gives deterministic NPU management by pre-allocating CPU headroom and allowing preemption for high-priority interrupts within microseconds. Watchdog-style NPU utilization monitoring triggers scheduler actions if overruns occur, such as demoting to a pruned variant, ensuring deterministic motor control or alarm paths remain reliable even during heavy inference. A unified vendor HAL and NPU backend ecosystem simplifies porting and preserves accuracy while cutting integration time dramatically. Frameworks like TensorFlow Lite Micro and ONNX feed backends that support int8, int4, and transformer ops, enabling teams to move from weeks of porting to hours while maintaining quantized accuracy above 98%. Software stack optimization combines offline compiler techniques like layer fusion and sparsity block detection with runtime scheduler exploits such as pipeline depth utilization and overlapping weight loads. Together, these approaches reduce memory movement, compress models significantly without accuracy loss, and yield up to 3 times the throughput compared to naive sequential execution on the same silicon. Efficient and secure model updates use delta-compressed weight patches sent over lightweight protocols like MQTT or LoRaWAN to minimize bandwidth. A secure bootloader verifies signatures and uses swap partitions with automatic rollback on CRC failures, while containerized model runtimes isolate updates so new functionality can be deployed rapidly without rebooting safety-critical threads. On-device telemetry forms a closed loop for adaptive edge ops by collecting inference, confidence, histograms, and logs, comparing live metrics to a golden profile, and applying KL divergence checks to trigger requantization. Anonymized digests uplink to cloud-side fleet retraining, enabling selective edge updates and continual optimization while respecting privacy and regulatory constraints. The NXPI MX8M Plus Edge Inspection Case shows integrated NPU vision, accelerating a dual 12MP camera pipeline to 200 frames per second, delivering processed OKNG signals to PLCs with roughly 5 milliseconds latency. By avoiding raw video uplink to the cloud, the solution slashes bandwidth needs, preserves proprietary imagery on-premise, and improves throughput and security. Coral Talk demonstrates ultra-low power multimodal AI for wearables, combining always-on keyword spotting, accelerometer gate analysis, and moisture-aware gesture switching around a sub-5 mW NPU. This enables seamless multimodal UX, a 40 mAh battery lasting days in always-on scenarios, and reduced recharge frequency while keeping form factor and responsiveness intact, turning NPU integration from a lab experiment into a scalable 2025 product follows 5 practical steps. Define measurable latency and power budgets. Select an NPU whose TOPS W maps to your model MAC count. Co-optimize graph and memory layout. Validate real-time coexistence early. And build OTA infrastructure before silicon production so updates and manufacturing scale smoothly.